In digital design, we are taught to view Boolean logic as a realm of flawless mathematics. We write equations assuming that when an input changes, the output evaluates and updates instantaneously. In physical hardware, that mathematical purity routinely breaks down. You can design a perfectly valid combinational logic circuit, flip a single input switch, and watch the output inexplicably stutter, generating a false signal before finally settling on the correct value. The root cause is that logic gates are physical objects built from silicon and metal. They take time to process voltage. In most systems, we mask these intermediate processing steps by introducing a global synchronizing clock. Removing that clock forces us into the domain of asynchronous sequential logic. In this paradigm, state changes are governed entirely by continuous input monitoring. There are no discrete ticks. The circuit reacts to inputs the moment they arrive. The perfection of Boolean logic is an illusion maintained by the clock. Stripping it away exposes engineers to the chaotic, raw physical reality of silicon propagation delays. The traditional synchronous finite state machine, or FSM, relies on a clock to act as a traffic light. The clock pulse forces the entire system to move in discrete, predictable steps. This protects the system. Between clock ticks, voltages fluctuate as they travel through varying lengths of wire and different logic gates. The clock period guarantees those signals have enough time to reach a stable voltage before memory flip-flops capture the final state. Left, synchronous FSMs depend heavily on clock lines. Right, asynchronous FSMs eliminate the clock and memory flip-flops entirely. Instead, combinational logic output routes continuously back into its inputs. Upon an input change, voltage cascades and instantly races back through this feedback loop. Engineers use this architecture because it achieves absolute maximum theoretical speed, limited only by the physical properties of the gates. It also consumes significantly less power by eliminating the massive clock distribution tree required to keep millions of transistors in sync. Asynchronous design trades the predictable safety of discrete time for the uncompromising speed of continuous physics. Every physical and, or, and not gate imposes a propagation delay. It takes a few nanoseconds for voltage to travel from the input terminal to the output. When a circuit splits an input signal across parallel logic paths, those pathways often have different total delays. These differential delays create momentary logic failures, called hazards. A static zero logic hazard occurs when a circuit's output is mathematically supposed to remain at zero during an input transition, but physical delays cause the voltage to momentarily spike to a 1. This Carnot map illustrates a static hazard. Two adjacent groupings of ones leave a boundary uncovered without a redundant overlapping term. When transitioning across that boundary, one gate turns off before the other turns on, resulting in a momentary spike to 1 before settling to 0. A dynamic hazard is a different failure mode. This occurs during a deliberate state transition, where the output is intentionally switching from a 0 to a 1, or vice versa. Instead of a clean transition, differing path delays cause the output to bounce multiple times, flickering 0, 1, 0, 1 before stabilizing. Downstream logic connected to this output will interpret these bounces as separate, valid signals. In clockless logic, proving the Boolean math works is insufficient. Designers must explicitly map the logic and add redundant gates to cover the physical time differentials and prevent hazards. Hazards cause momentary output glitches. Races cause permanent internal state failures. The internal state variables of the FSM, usually denoted as Y1, Y2, and so on, hold the system's memory by routing output signals back to the inputs. A race condition occurs when a single input change requires two or more internal variables to flip their states at the exact same time. For example, transitioning from 0, 0 directly to 1, 1. Perfect simultaneous transitions across different silicon pathways are a physical impossibility. Resistance and capacitance vary at the microscopic level. This speed mismatch forces the system into an unintended transient intermediate state. The variables will hit 0, 1 or 1, 0 before they both reach 1, 1. In a non-critical race, the logic is designed so that the intermediate state still directs the FSM to the correct final destination. The system recovers. A critical race occurs when that intermediate state directs logic into a completely different feedback loop. The FSM becomes permanently trapped in the wrong final stable state. Without clock pulses to enforce uniform, parallel updates, simultaneous variable changes become a physical race where the slower signal crashes the entire system. To harness asynchronous feedback loops without triggering races or hazards, engineers must adhere to strict rules. The most critical operational constraint is called fundamental mode. The first rule of fundamental mode dictates that only one input variable is allowed to change at a time. The second rule requires the system to fully process that single input change and reach a completely stable state before the next input is allowed to arrive. To design logic satisfying these constraints, engineers use a specific mathematical tool, the asynchronous flow table. This image contains a traditional Moore state table. Synchronous design maps out safe jumps from present state directly to next state, assuming the clock handles the transitions. Unlike synchronous tables, an asynchronous flow table explicitly maps the journey through unstable states. Circled entries indicate stable states. First, an input change causes horizontal movement to an uncircled, unstable state. Second, internal variables react, causing vertical movement down the column until locking on to a circled, stable state. The flow table serves as a conceptual map. It allows engineers to explicitly chart safe, predictable logic routes through the inherently unpredictable delays of physical silicon. In practice, asynchronous logic is deployed for specific boundary conditions, such as physical switch debouncers or localized interrupt controllers. These components interact directly with unpredictable external events. They cannot afford to wait for a system clock cycle to register an action. When a physical metal switch is flipped, the contacts literally bounce against each other. This creates a chaotic, jagged electrical signal that spikes up and down over several milliseconds. An asynchronous combinational circuit does not sample the line. It reacts instantly to the very first rising edge of that jagged voltage spike. Because the circuit obeys fundamental mode, the unclocked feedback loop immediately locks the logic into a stable state. It processes the action and deliberately ignores the subsequent mechanical bouncing. For these localized tasks, asynchronous logic provides a physics-driven responsiveness that synchronized polling systems cannot achieve. If unclocked logic is so fast and power efficient, why aren't modern multi-core processors built entirely asynchronously? The bottleneck is synthesis. Modern electronic design automation software struggles to map out large-scale unclocked systems. To build a functional asynchronous chip, designers must mathematically calculate and bound the precise physical delay of every single wire and logic gate across billions of transistors. Testing these designs is a severe engineering challenge. You cannot simply slow down or pause a clock to step through a bug, because the physical timing itself constitutes the logic. Synchronous logic relies on abstraction, using time to mask physical imperfections. Asynchronous logic strips away the abstraction and relies entirely on raw physical mechanics. Because of the intense verification required, synchronous clocked systems remain the standard for massive system-on-chip integration. True mastery of digital design requires knowing exactly when to rely on the safety of a synchronized clock and when to cut the wire, embrace the instability, and engineer